Okay, begin by importing Tensorflow as TF. Then we import the MNIST dataset by writing from tensorflow.keras.dataset import MNIST. And the MNIST is a dataset of 70,000 handwritten digits and their appropriate labels, which indicate if they are a digit from 0 to 9. Now it's time to load the training images and the test labels from MNIST as well as their labels. You do this by loading first the train images and their labels, then the test images and their labels, and then you set that to the loaded data from MNIST. Now finally, all pixels in the train and test images need to be divided by 255, so each pixel has a activation of 0 to 1. This is important for the neural network to be able to process it. Nice, we have our data now and it's time to compile the model itself. For our model, we are going to have 4 layers. An input layer, 2 hidden layers, and an output layer. Our first layer is the input layer, which will be the actual image we insert into the model. Given that all images in the MNIST dataset are 28 by 28 pixels, we are going to convert that into a flat array of pixels, which would be a total of 784 neurons or input pixels, whatever you want to call them. So let's begin by making our first layer. First, you want to define the model as a sequential neural network by writing model equals tf.keras.models.sequential. Now we are going to make our 4 layers. We are going to begin by making our flattened layer by writing tf.keras.layers.flatten, and then we're going to select that the input shape is 28 by 28. Let's do it. Now it's time to make our first hidden layer. We're going to make a dense 128 wide layer that uses the ReLU activation function, which is an activation function that returns normal values for all positive numbers but returns 0 for any negative number. And a dense layer is a layer of neurons where all neurons are connected to all other neurons. Let's do that. For the second hidden layer, we are introducing a dropout layer which alters the value of all neurons going through it by 0.2, and this prevents the model from learning the training data and having a hard time generalizing for the testing data we are going to use later. It's important to note that it's still learning, but we don't want it to only learn the training data and its noise. We still want it to be able to understand new data as well. Let's do that too. And finally, we are to the output layer. This is the actual predictions the model will make. We will have 10 neurons, each one representing its own digit, and we will use these neurons as predictions of what the model thinks it's looking at. We will also use the softmax activation function, which will make sure that all of the outputs summarize to 1, and we simply choose the highest outputted neuron. Let's write that too. Now it's time to compile the model. We will be using the Adam optimizer, which basically is an optimizer that aims to minimize loss, our loss function being this sparse categorical cross entropy function. And loss, it simply means how much the model is adapting in every step it takes towards learning. The lower the loss, the better the model, because it has to change less to be right. Finally, we will measure the success of the neural network in a percentage of accuracy. And hey, the model is done. Now it's time to train it, or fitting it to the data, and we're also going to evaluate it on the test images and the test labels once it's done training. Here we are fitting it on the train images and their labels, and we are training it for 5 epochs, which basically means that we are iterating over the dataset 5 times. And for the test loss and test accuracy, we are going to evaluate the model using the test images and the test labels to get those, and then we're finally printing the test accuracy. And now the script is done. You'll see that you can run the script if you don't see any errors, and then you'll see the accuracy for each epoch and the final evaluation accuracy for your neural network. Thank you for watching. Goodbye.